For part 2 of linear kinetics, we are going to talk about the conceptual application of Newton's second and third law, including impulse, momentum, and the law of gravitation. So Newton's second law is the law of acceleration, and it states that if a net external force is exerted on an object, the object will accelerate in the direction of the net external force, and its acceleration will be directly proportional to the net external force and inversely proportional to its mass. So Newton's second law is otherwise known as F equals ma. So we can see here that if F remains the same, m and a will be directly inversely proportional to one another, and acceleration will be directly proportional to force. So again, mathematically, Newton's second law can be written as the sum of all of the net forces is equal to the mass of the object times the acceleration of the object. Conceptually, Newton's second law is interpreted as a cause and effect relationship. So the force causes the acceleration, and the acceleration is the effect of the force. So mass is always going to be constant, right? Unless we are talking about a perfect inelastic collision, as we talked about in the first part of this lecture. So if mass is constant, acceleration is what's going to actually be the effect of the force acting on an object, or otherwise it is going to be what is changed by the force acting on an object. To continue this interpretation, we know that if a net external force acts on an object, then the object will accelerate in one direction or another. Rephrasing that, we know that if an object is accelerating in a positive or negative direction, there must be a net external force that is acting on the object to cause the acceleration. So our net external force is not equal to 0. It does have some type of magnitude in one direction, positive or negative, to cause a change in acceleration. So in applying Newton's second law, if we take an example of lifting a 4.5 kilogram bar up in your hand, the bar weight would be approximately negative 45 newtons, because that weight is going to be acting down against you, right? If the bar is at rest, acceleration will obviously be 0, and the sum of net forces will be 0. So to move the bar, your hand force on the bar must be positive 45 newtons, or actually over 45 newtons, to start raising the bar. It has to be greater than 45 newtons because we have to overcome that weight, meaning the force and acceleration due to gravity. So to keep the bar moving upward at a constant velocity, your hand force must be equal to 45 newtons. So to bring the bar at rest at the end of your lift, your hand force must then be negative 45, or not negative 45, less than positive 45 newtons, because it has to come to a stop. And then obviously to keep the bar at rest at the top of the lift, your hand must be equal to 45 newtons. Taking another example of simply rolling a 4.5 kilogram bar on the floor, this is going to be a lot easier, right? The amount of force needed to overcome the bar at rest is going to be smaller, because we simply have to be greater than the force of friction. So to keep the bar rolling across the floor, your hand force must be equal to the friction force. So to stop the bar rolling across the floor, your hand must create a force that resists the motion of the bar, or is greater than the force of the motion of the bar. So to simply keep the bar from rolling on the floor, your hand force can be 0, because at this instant, if the bar is at rest, as long as there is no incline on the floor, there is no horizontal force acting on the bar. In using F equals ma, a is relative to acceleration at an instant in time. But typically with sport and human movement, we are more concerned with the final velocity after some type of external force acts on an object over a period of time rather than a specific instant in time. For instance, if we're talking about a baseball pitcher or a softball pitcher, we're typically more concerned with the velocity of the ball after the duration of the pitch. So what we can do here to look at average net force instead of a force or acceleration at an instant in time, we can substitute acceleration equals velocity over time to the change in velocity over the change in time. So this will then give us average net force instead of instantaneous net force. So mathematically rearranging F equals ma into this first formula here of the sum of forces is equal to m times change in velocity over change in time, we then multiply each side by time, rendering force times change in time is equal to mass times velocity, the final velocity minus mass times the initial velocity, or what we know is momentum here, okay? So what you need to know is that force times time, or the product of force and time, is equal to impulse, okay? So this is what's going to give us our impulse momentum relationship, where we know that the impulse produced by a net force acting over some duration of time causes a change in momentum, all right? So the impulse produced by this left side of the formula causes a change in momentum over here on the right side of the formula. So again, impulse is the product of average force and duration of force application, or the sum of forces times delta t. So impulse causes a change in momentum of a body that it acts on. Mass is going to be constant, so impulse is what changes the velocity of some object. So based on this F delta T is equal to M times Vf minus Vi formula, we know that a large force over a short amount of time, so a great force over a short amount of time, or a small force over a large amount of time, or any combination of force and time with the same product, is going to render an equal change in momentum or change in P. So the task in many sports skills is to cause a large change in the velocity of something. So in throwing events, the ball or the shot or discus, javelin, whatever, has no velocity at the beginning of the throw, and your goal is to give it a fast velocity by the end of the throw. So essentially we want to increase the object's momentum. In striking events, like with a racket or a bat, this object has no velocity at the beginning of the swing, and the task is to give the implement a fast velocity prior to impact of the object. In jumping events or some type of propulsion events, our bodies might be the objects that we want to increase the momentum. So in all of these activities, though, the techniques used can be explained by, in part, the impulse and momentum relationship. So a large change in velocity is produced by a large average net force acting over a long time interval. So in order to increase momentum of an object or a bat or yourself, because there are limits on the forces that humans are capable of producing in general, many sporting techniques involve increasing the duration of force application in a specific direction in order to increase one's momentum and their velocity overall. So the same principle can be applied in cases in which you want to decrease momentum, or you want to slow an object down, decrease its velocity, or stop an object, even getting that velocity to 0. So these instances would be in the case of catching an object, or even your body landing safely. So in catching and landing and other impact situations, in which the goal is to decrease magnitude of momentum, you want to decrease the magnitude of the impact force in order to increase safety of performance, especially in landing itself. So by increasing the duration of the application of the impact force, or increasing delta t, the impact time, all right, we will decrease the average impact force. So, sorry about that. So, if you increase delta t, then the main F, or the main impact force, must be reduced. All right. So, again, whether you want to increase or decrease momentum, this impulse momentum relationship is a key factor in the techniques that we use, especially in sport performance and human movement overall. And moving on to Newton's third law, the third law is the law of action and reaction. So if an object exerts a force on another object, the other object exerts the same force, but in the opposite direction. So we can generally think of Newton's third law as the law of equal and opposite. So the law of action and reaction: for every action, there is an equal but opposite reaction. So there must be two bodies involved when a force is exerted. So interpreting this third law is that the force on each object is the same size, but in opposite directions, or in other words, they are mirrored pairs. So this holds true even when bodies are significantly different in mass, which is the effect on each body is explained by Newton's second law in the F equals ma, and even furthering that into the momentum impulse relationship. Moving to the law of universal gravitation, this states that all bodies are attracted to one another with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. Now, when Newton came up with this law, this overall states that every object has some type of gravitational pull towards another object. In sport and human movement, these pulls are always very, very small, so small that we can typically ignore them in our calculations. However, one gravitational force that has to be considered, because it plays a major role in sport and athletics, is obviously the gravitational pull due to the Earth itself. So mathematically, the force of gravity is equal to the gravitational constant, or 9.81, times the mass of one body, which could be a ball or a person, here the object of analysis, plus the mass of the other body, or the mass of the Earth, over r squared, which is going to be the radius of the Earth, or the distance between the bodies. So for earthbound skill situations, G and M sub s and R are always constants here. So gravitational force is proportional to the object's mass. So the weight of the object is obviously W equals mg, where g is 9.81 meters per second squared to the center of the Earth, or the gravitational pull towards the center of the Earth. So that is the end of our linear kinetics chapter. Hopefully this second part provided some good conceptual information for Newton's second and third law.